Learning Outcome 8.2. Determine the time signal and spectrum for amplitude modulated signals. In Chapter 7, you were introduced to the process of sampling, and we started by looking at that in the time domain. There we had an input signal that was multiplied by another signal. We looked and determined what its output signal would be. Amplitude modulation is similar to that in being a signal multiplied by another signal. But this time, our signal, instead of being an impulse train, is a sinusoid, particularly a cosine. But since it can, in theory, have any phase, we use it as a cosine. This is also called sinusoidal amplitude modulation. So what's the response to this? What do we get out? So let's look at that modulating signal, C of t. It has amplitude 1, one's a period, 1 times our signal x of t is just going to be our signal at those points. Back to our modulating signal C of t, in between those amplitudes of 1, it has amplitudes of -1. -1 times our signal would be negative x of t. So at those points, we have the negative of x of t. In between all of these, our modulating signal has an amplitude of 0. 0 times anything is 0. So at all those places, our resulting signal will have an amplitude of 0. In between, it will take on values between x of t and negative t, so we can play connect the dots. And that's the result of sinusoidal amplitude modulation, where you can see our original signal on the top, the negative of it on the bottom. If we take a higher frequency signal, C of t, we can do the same thing. And now it's a little bit more obvious, seeing our original x of t signal on the top and our original negative x of t signal on the bottom. And we call those an envelope function, because our signal fits nice and snugly between the two. Okay, let's look at this again. But instead of looking at it in the time domain, let's look at it in the frequency domain. Similar to in Chapter 7, we will consider that our input signal is a band-limited signal, which means that its spectrum is non-zero only within a certain band. We're considering x of t to be a real signal, therefore its spectrum is symmetric about 0. Every component of this process exists also in the frequency domain. So if C of t in the time domain is cosine omega 1t, what is C of j omega? Go look in table 4.2. Pi times the quantity delta of omega minus omega 1 plus delta of omega plus omega 1. Draw that on your paper. What does it look like when you plot it versus omega? Two impulses, one at omega 1, one at negative omega 1, both with an area of pi. Area because this is continuous. So these are arrows and the amplitude is infinity, but the area is pi. Now if we multiply these in the time domain, what are we doing in the frequency domain? 1 over 2 pi convolution. When we convolve something with an impulse, applying the shifting theorem, we're just going to shift what we had to a different place. We have our 1 over 2 pi factor, the pi that comes from our cosine, and our x of j omega will be scaled by that quantity. So we're going to have x shifted to the location of omega 1. Each of these frequency values is incremented by omega 1. Then for our second term, each of our frequency values is decremented by omega 1 because our impulse is at negative omega 1. When we take this amplitude scaling factor, we have the 1 over 2 pi from the convolution, the pi from the cosine, and 1 from our original spectrum. It will not always be 1, but here we're starting with 1. Therefore, our new amplitude is 1/2. Okay, what do we need to put as conditions on omega 1 and omega m so these two do not overlap? What value has to be greater or less than the other value in order for these two triangles not to overlap? We need to have negative omega 1 plus omega m to the left of omega 1 minus omega m. Therefore, negative omega 1 plus omega m has to be less than omega 1 minus omega m. With a little bit of algebra, we wind up with a condition that omega 1, the frequency of our modulating signal, has to be bigger than omega m, the maximum frequency present in our original source signal. Make sure that you can do this operation and draw this yourself with everything labeled, all the frequencies, including the amplitude. In this chapter, you will do this many, many, many times. And you need to get to the point where you can draw this almost automatically. You got an introduction to this in chapter 7, going through these processes. Now's the time to perfect that.